able to jump to the analyze stage, right? But of course, after some steps, okay, for example, elementary row operations, augmented matrix, and something like this, okay, so you will arrive at some point, and then you can decompose the case of value A, okay, and then to discuss the answer, okay, or the solution nature for this system. Okay, so promise me, okay, to go through this practice, okay, I deeply believe that, okay, it will be very beneficial for your understanding for this topic. Okay, and then I would like to start from a important application or extension from Gaussian elimination, which is called Gaussian Jordan elimination. Okay, this is our starting point of today. Okay, so if you are ready to go, so we will start from page 17. Okay, so in this section, okay, section 4, we are going to extend, okay, the application of Gaussian elimination. Okay, in particular, we would like to use, okay, Gaussian elimination or Gaussian Jordan elimination, okay, to find out the inverse of a matrix. Okay, inverse of a matrix. Okay, of course, okay, you will see why. I will tell you why or what is the motivation we need to or we should equip this kind of techniques, okay, on our own, okay, in order to find out the inverse. Okay, so stay tuned for this. At the very beginning, okay, to facilitate the subsequent discussion, I firstly assume there is a matrix A, okay, 3 by 3 matrix A. Okay, it takes the following form. Okay, of course, there are line entries for the 3 by 3 matrix. And now, okay, our objective is to find out the inverse of matrix A. Of course, you may say that, hey, Patrick, in topic 2, we already discussed how to find out the inverse of matrix, right? By using the inverse formula, right? And it involves a determinant, adjoint matrix. In particular, okay, it involves cofactor and transposition, right? And so on and so forth, right? So honestly, to me, I also think this method, okay, is quite tedious. Okay, it's quite tedious. And also, if you think that whenever the size of the matrix is particularly large, for example, 10 by 10 matrix, okay, 12 by 12 matrix, okay, or something even bigger, okay, but okay, let's forget this. Okay, even the 10 by 10 matrix, okay, it also gives you a headache, right? Okay, so by seeing this, okay, we are motivated to find out another method, okay, probably more effective or more easier method, okay, to find out the inverse of the matrix. And this is the focus of today. Okay, I would like to develop some effective means, okay, to compute, okay, A inverse by using Gaussian elimination and its extension, Gaussian Jordan elimination. So let's take a look at the following development. In order to find out A inverse, okay, I firstly assume that A inverse will take the following form. Okay, so here you can see that when you assume A is a 3 by 3 matrix, naturally you can also simply assume you can simply write down, okay, the dimension of the A inverse to be a 3 by 3 matrix as well. Okay, otherwise you cannot compute it, right? Okay, so when you assume this is a 3 by 3 matrix, naturally the inverse of matrix A is also 3 by 3 matrix. So in general, if you have a n by n matrix A, so the inverse of this matrix A will also be an n by n matrix. Okay, so is it clear? Okay, so let me see. Let me put it down. Okay, in general, okay, if A is n by n matrix, okay, A inverse is also n by n matrix. Okay, so I hope this is also clear for you. Actually, this is just a recap, okay, for what we have discussed and learned in topic 1 and 2. All right. Okay, now A inverse, okay, basically, okay, A inverse is available now. And now I would like to apply the identity, okay, for the matrix, which is A times A inverse equals identity matrix I. Okay, so we get something like this. Okay, I simply replace A and A inverse, okay, by what we have defined it previously. Okay. Okay, I will tell you more information. Okay, and this guys is identity matrix on the left and the right hand side after the equal sign, right? So to make it more clear, okay, I simply connect them for you. Okay, so this guy, the first matrix is matrix A. Second guy, this is not clear. Okay, this is not sharp enough. Maybe this one. This is not good. Okay, this one. Okay, so this guy is A inverse. Okay, a similar extent from the identity only. Okay, and not to mention, okay, the last guy is identity matrix I. Okay, 3 by 3 matrix. Okay, now, in order to find out the A inverse, what we want to do is to find out all of the value x11, x12 until x33, right? So our job, our key for this problem is to find out all of the xij. Of course, ij will take the value 1, 2, 3. Okay, that means we are going to cover all of the value of x. Okay, in particular xij. Okay, all of the xij we want to find out, or we need to find out in order to complete the computation for inverse of the matrix A. Okay, and now I would like you guys to have a look. Okay, when you try to expand, okay, the left hand side of the red equation, the red matrix equation, actually we can see there are actually 3 linear systems associated with this red equation, matrix equation. Why do I say so? Why do I say so? So let's take a look at the following discussion. Okay, and then by using this, okay, by seeing this discussion, okay, of course you will. I believe you guys will be able to see why we can say we have 3 linear systems, okay, at a time. So let's take a look. Suppose that I focus on this column. Suppose I would like to expand, okay, or to break the matrix, okay, the matrix multiplication, okay, along the first column. So what we get, okay, 0 times x11 plus 2 times x21 plus 0 times x31 equal 1. Secondly, 1 times x11 plus 0 times x21 plus 4 times x31 equals 0. The last equation, or the third equation, 0 times x11 plus negative 2 times x21 plus 1 times x31 equals 0. Okay, so indirectly, we seems that we are having 3 equation, right? And then we can consider this guy, okay, will form a linear system. In particular, the variable are x11, x21, and x31. So you can see that if we write in matrix form, actually it represents something like this. So you can see, I hope you can connect, okay, the current result, okay, the current result with this guy, okay. Do you agree they are the same? Okay. Do you agree they are the same? Okay, right. Okay, so that's why, okay, I would say when you try to consider different column in okay, in these 2 parts, okay, you will get 3 linear system at a time or at the same time, right? Okay, so when you extend, okay, to consider the second column, use another color maybe, purple one maybe. Okay, when you come up, okay, when you consider the second column, okay, so you will get, okay, this matrix. For the third column, okay, you will get, okay, the matrix like this. Okay, so at this moment, okay, can you see what I mean? Okay, and how and why you can get 3 linear systems at a time. Okay, this is very essential. Can you convince yourself and understand what I'm talking about? If it is fine, okay, so let's move on. And now we are here, okay? At this moment, okay, we convince ourselves that, okay, we can indirectly form 3 linear systems at a time. But, okay, how to play with that? Okay, the next question we are going to address now. Okay, suppose we want to focus on the first matrix, okay, in blue circle, okay, in blue circle. So I simply copy down here and then write in a augmented matrix. Okay, so nothing new here. Okay, just convert this first matrix, okay, and the first system, okay, as an illustrative example, and then the second one and the third one, okay, will naturally directly, okay, apply the idea studied here. Okay, so I simply convert the first system into augmented matrix. Okay, and then as usual, okay, here, don't forget, our key is to find out, okay, variable x11, x21, and x31. Am I correct? Okay, so this is the key for the first system. And our job, okay, is to apply what we have learned in the last class, okay, by using Gaussian elimination or the associated technique, for example, backward substitution, many things, right? Okay, we would like to carry out the following analysis. Okay, firstly, okay, we start from this guy, okay, and then I would like to change it to REF or RREF, right? Okay, so maybe I first stick to the REF first, okay, and then I move from the first matrix to the second matrix, okay, and then we apply the elementary row operations. Can you tell me what kind of elementary row operation we applied? I simply flip the order of the first row and the second row, right? Okay, so row 1, row 2 is flipped or is exchanged, right? Okay, and then I would like to take a step further. Okay, I move from second matrix to the third matrix, and we seems that, okay, we use R2 put R3 to update R3. Okay, of course, I'm not doing it randomly. Okay, of course, we observe something. I hope you can still remember why I always put, okay, the left-hand corner, okay, to be 1. Okay, in order to enjoy the echelon form, right? Okay, so that's why, okay, we enjoy the first step. Okay, the secondly, okay, we see that, okay, we want to eliminate some entries in the variable. Okay, so we use R2 plus R3 in order to update R3, right? And at this moment, okay, we arrive at a intermediate result. Okay, so now can you tell me what kind of echelon? Is it an echelon form, or can you tell me is it a row echelon form or a reduced row echelon form at this moment? This is REF. Very good. Very good. Why? Okay, you can at least you can spot 2 things. Firstly, this is not leading entry 1, right? Secondly, there is another number over there. So for that particular column, okay, the leading entry is the one and only one entry of that column, right? For RREF. So at this moment, we can only say this is in REF only. Okay, but why do I say so? Why do I say so? Okay, you will see. Previously, okay, until that point, okay, we may use the Gaussian elimination and the backward substitution to find out all of the variable for the given linear system, right? And now I would like to show you one. I would like to say that, okay, if we take a step further, okay, I would like to introduce a new approach, okay, to tackle the system more easily or more effectively. So let's take a look. I'm not satisfied with the current result, okay, the current REF result, and I would like to carry out a several steps of the elementary row operations, and I would like to achieve, okay, the left-hand side of the augmented matrix to become RREF. Okay, I would like to make, okay, the left-hand side of the augmented matrix further become RREF, reduced row echelon form. Why do I say so? Why do I do that? Okay, because if we can further transform the augmented matrix into RREF, okay, so this is RREF, okay, you can check that. Okay, but before that, okay, let me tell you how to arrive at the RREF, okay, for as a review or as a recap, okay, whatever you want. Okay, so I simply copy everything here, okay, and then I would like to firstly divide the second row by half. I mean, not by half, okay, by 2, okay, or you may say you multiply half, okay, to the second row, okay, so maybe I simply row 2, sorry, okay. I multiply 1/2 or 0.5, okay, to the second row in order to make this entry to be 1. Okay, so you can see the corresponding entry is also updated by this factor, right? Okay, it's a step closer to the RREF, and from the current step to the last step or to the next step, okay, I would like to use -4 times R3, row 3, okay, plus the first row in order to update the first row. Okay, and then we achieve, okay, the augmented matrix here. I believe you guys should be able to tell me this is already in RREF, right? Okay, even though you cannot, okay, you don't need to tell me. Okay, go back to check the idea and the definition. Okay, but I can tell you this is already in RREF. Okay, okay. So you may have a question. Okay, hey Patrick. Even though, okay, now I know this is RREF, so what is the advantage, or why do we need to spend some effort, okay, to arrive at RREF? I'm going to tell you the answer. By doing this, the left-hand side of the augmented matrix already in RREF, right? Okay, RREF. And the advantage is that we can spot the answer, right? We can spot the answer, okay, directly. And okay, I would say actually very easily, right? Now you can tell that for the first system, okay, the variable x11 equals -4. The second variable x21 equals half, and the last one x31 is 1, right? So let me repeat, okay, why we want to take quite a number of steps until RREF, because we would like to see the solution directly and very easily, right? In the last class, I remember a classmate mentioned a very good question. Why don't we get to the RREF? Yes, we should, or I would say it would be preferable, okay, to arrive at RREF, okay. But in that particular example, I would like to tell you that to achieve RREF may not be always feasible or easy to do that, because when you check with the previous example, it involves in K, right? It involves in K. Okay, so you can see that RREF is preferable, but may not be easy or may not be practical to achieve. Okay, so we to strike a balance, okay, on the speed of the computation or many things. Okay, so we may choose to use the RREF, okay, as a remedy, okay, and then to do the to carry out the analysis. Okay, so I hope you can see, okay, RREF is preferable, okay, but it's subject to the situation. Okay, if we involve some parameter inside the system, it may not be easy for us to achieve RREF, or it will involve quite a number of efforts to achieve RREF. But the question is it worthwhile to do that? Or if we stick to REF, okay, maybe we can start the analysis more easily or more effectively. Okay, but if we can do the RREF as our final step, I would say it is more preferable. Okay, it is more preferable because the advantage is that we can spot the answer directly, right? Just like the current case. So I hope you guys will understand the logic. Okay, why I introduced REF first, and until here I just introduced RREF. Okay, and then I see there's a question from the chat room, and I'm super happy and appreciate for the classmate to answer the question for us. Okay, because you can see that there is a number 4 here. Okay, and this is not the only entry for the leading in the particular column, except the leading entry, right? So the second last step is not RREF. Okay, and that's why we have to use the last step to form, okay, or to formulate the RREF. Okay, so far so good. Okay, and here, okay, I just want to tell you the motivation of Gaussian-Jordan elimination. All right, so far so good. Okay, and then, okay, let me introduce this to you. And the current, until this current step, okay, all we do is the technique, which is called Gaussian-Jordan elimination. Okay, so far so good. Okay, the step until here, or the techniques until here, okay, we call it Gaussian-Jordan elimination. Okay, so far so good. Okay, so let's move on. Okay, we are in page 18, and then we move to page 19. And now, I would like to tell you further, okay, on this observation. And now, of course, you can tell, okay, the variable x11, x21, x31 to be the corresponding number. Now, I would like to, of course, you can also solve the remaining 2 systems. Don't forget that, okay, you still have 2 remaining systems, okay, to be solved, okay, but they can be done in a similar manner. Of course, you can also play with the RREF, right, and then tell the answer directly. Okay, I leave it for you, okay, as exercise or as practice, okay. And here, I just want to tell you the inverse matrix can be done by using this method. Okay, suppose now we are done for the 3 system, and then we input, okay, to corresponding value for x11, x12, until x33, right? Okay, into the original matrix A inverse. So we can form, okay, the inverse matrix like this. Okay. So you may think, okay, this is yeah, maybe this is another way for us to find out A inverse, but are there any special thing over there? Okay, this is interesting to I would say there is an interesting result. Okay, I would like to share with you. Okay, from previous page, okay, the last matrix, augmented matrix in RREF, right? You can see that, okay, the left-hand side of the augmented matrix is in identity matrix, right? Am I correct? Not to mention, okay, if you solve, okay, the remaining 2 system, I believe you guys will also achieve RREF, right, in the final step, and then you will get the left-hand side of the augmented matrix of the remaining 2 systems to be identity matrix, right? Okay, so this is a very interesting observation. We can see that the left-hand side of all of the augmented matrix are the same, and in particular, all of them are identity. Oh, sorry. Identity matrix I, right? Okay, I consider separately. Okay, I consider separately. Okay, is it okay? I consider separately. Okay, but if you solve the system one by one, you will see that, okay, all of the augmented matrix on the left-hand side of all of the augmented matrix all becomes identity matrix I. Okay, and okay, I would like to enjoy this property. But before that, I would like to correct a typo for you. Okay, so if you are careful enough, okay, you can see that these 2 entries, okay, typos, okay, they should be, okay, half, okay. Okay, please help me to correct the typo. Oh, at the same time, okay, we have a we have one classmate to spot this. Thank you very much. You're right. Okay, because you can see that. Okay, this is half, right? So please help me to correct the typo and keep it yourself. Okay, so get back to the discussion so far. We spot an interesting result. All of the augmented matrix after simplification by the elementary row operation, right? All of them will become I. Okay, starting from, okay, A. And then after finished a series of elementary row operation, on the right-hand side of this augmented matrix, it is nothing but the inverse matrix A, right? Okay, okay. So by doing this or by observing this, okay, we have the following observation. Whenever we want to find out the inverse of a particular matrix A, okay, we can always consider, okay, an augmented matrix like this, okay, an augmented matrix like this. On the left-hand side of the augmented matrix or on the left-hand side of the vertical bar of the augmented matrix, we simply put down the matrix A here. On the right-hand side of the vertical bar in the augmented matrix, I simply put down identity matrix I, okay. After applying a series of elementary row operations, okay, of course, quite a number of steps, okay, quite a number of steps. Okay, finally, we arrive at the form like this, okay. Another augmented matrix, on the left-hand side of the vertical bar of the augmented matrix, it becomes I. It becomes I, identity matrix. On the right-hand side, this is what you want, the inverse of matrix A, okay, will be formed here, okay. So this is the description, okay, verbally, okay. So I also want to write in this way, okay. Okay, finally, okay, we get something like this. Of course, here, okay, we have a number of elementary row operation. Okay, so to visualize the idea, okay, you may refer to this part, okay, to visualize the idea, okay. The previous discussion, okay, it is available for verbal only. Okay, so in order to find out inverse matrix, okay, inverse of the matrix, okay, I suggest you guys to take a look, okay, this method, okay. Okay, this is the starting point, okay, this is the starting point. You write down the augmented matrix consists of two parts. On the left-hand side, put down the matrix A, okay, the coefficient matrix. On the right-hand side, okay, simply put down identity matrix. And then for the whole matrix, you carry out a series of elementary row operation. Of course, many steps. I don't know how many steps, okay, but after several steps, when you arrive at a pattern like this, okay, an augmented matrix, on the left-hand side, you get identity matrix, and on the right-hand side, you get a new matrix. Okay, so basically, you are done. Okay, you are done to find the inverse of matrix A, because on the right-hand side of this augmented matrix, it is already the inverse of the original matrix A. All right, so this is the logic or the rationale behind this method. And that's why, okay, I need to introduce Gaussian-Jordan elimination, because I would like you guys to arrive at the identity matrix, right, in the augmented matrix. Okay, so I hope you can see the connection. Why we put, okay, Gaussian-Jordan elimination, okay, after Gaussian elimination, and then to find how to find the inverse, okay, by using Gaussian-Jordan. All right, so this is the logic. So far, so good. So far, so good. But at this moment, you may have another question in mind. Hey, Patrick. Okay, even though I know Gaussian-Jordan elimination is good, okay, for us to find the inverse, but Okay, but how can we apply, okay, or what is the importance? Why Gaussian Jordan is important? In other words, why inverse of a matrix is important? You keep mentioning, okay, how to find out inverse of a matrix. What is the importance among them? So let's take a look at the following discussion. Consider a linear system. Okay, consider a linear system like this, and we write down the matrix equation form: A times X equals B. In particular, A is a coefficient matrix. Okay, as usual, okay, A is the coefficient matrix, so-called, and X is the decision variable matrix. Okay, it consists of quite a number of variables in a linear system, right? I simply put it in one matrix. We call it a matrix of decision variable only. B is a constant matrix. A matrix consists of constant term, okay, for different equation. So don't forget that, okay, we need to assume, okay, or we need to consider, okay, the inverse of matrix exists, okay, such that the following two relationship, okay, or the identity holds, okay. And now I would like to tell you why A inverse is important, or is very helpful for us to find out the solution of the system, okay. So let's take a look. Let's consider the following situation. In the very beginning, I consider AX equals B, right? So this is the matrix equational form, right? Suppose A inverse exists by using the condition, right? Okay, A inverse exists. I would like to multiply A inverse on both sides of the equation, or on the left-hand side of the equation. Okay, can you tell me what is this? Can you tell me what it is? It is nothing but identity matrix, right? Okay, so I take one more step. Okay, I write it clearly. On the right-hand side, seems that I don't have too much room, okay, to simplify. Am I correct? Okay, so I simply keep it A inverse times B. Okay, but for the left-hand side, okay, it becomes I times X. Of course, don't forget, X is a matrix, I is also a matrix. Okay, don't forget, okay, or don't write down 1 here, okay. Okay, so otherwise it will lead to a wrong concept. Okay, but anyway, okay, I times X, okay, I simply drop matrix I, okay, and then we get something like this. Something like this. So now, can you recall what is meant by X? Can you remember, or can you recall, and can you tell me what is meant by X? This is the solution of the system. And this is particularly the key, okay, we want to solve for the system. Am I correct? So basically, okay, if we can solve A inverse, or if we can find A inverse by effective or easy way, so we will be able to solve the system, okay, very effectively, indirectly. Am I correct? That's why, okay, we develop, okay, at least two methods, right? Okay, to find out the A inverse, or the inverse of the original matrix A. Am I correct? And I hope you can convince yourself why you need, or you should learn this. Okay, why you need to learn a Gaussian Jordan elimination, and then we extend it to the way we find out the A inverse, because we want to find a effective ways to solve the system. That means we want to solve for X, okay, the key, right? Okay, we want to solve X for the system, okay, and this is why, okay, I would like to solve for the system of the linear equation. That means we want to find the value of X, right, or the vector, or the matrix of X, or the corresponding entry inside the matrix X, right? Okay, so this is the central focus of this topic. But we rely on A inverse, right? We rely on A inverse. So if we can find A inverse easily, that means the solution of the system can be found easily, right? Okay, I hope you can see the rationale behind. And then, okay, so to conclude this section, okay, I hope at this moment you should be able to see why we keep on using A inverse as our focus. Okay, and then if A inverse exists, and then we can compute A inverse by effective ways, method, say Gaussian-Jordan elimination. Okay, so we will be able to compute the solution of a system, okay, very effectively or very efficiently. Okay, so this is the idea why we keep on using those ideas. So far so good? Or is it clear? All right. So for this part, I didn't provide you with any particular example, okay, because we use it as a discussion, right? Okay. We also use it as an illustration how to arrive at the Gaussian-Jordan elimination, right? And how to arrive at the inverse matrix A. So I didn't provide a further example for this, but I hope you guys still remember there are two more linear systems to be solved, right? Here, okay? So you may treat it as a practice, okay, to see how to use the Gaussian-Jordan elimination idea, okay, to solve for the remaining variable, right, of the so-called two linear system, okay, and then to finalize the value for the A inverse, okay. So I didn't provide further example in this regard, okay, but there is a practice. There are two practice questions, okay, in the following. So if you have time, okay, try to take a look and then to see whether you can solve the problem accordingly. All right. Okay. So far so good. So far so good. Okay, if no particular question, okay, I will move to the last section of this topic. Okay, I will move to the last section of this topic. Okay, before the Q&A, okay, I would like to finish that part first. Okay, so okay, this page 21. Okay, I will leave it to you guys. Okay, so let's move to the page 22. The last section of this topic, okay, which is called Cramer's rule. Cramer's rule. Okay, Cramer's rule. Maybe some of you have learned this before, and for this method, for this rule, it is to help us to find out the solution. Okay, the unique solution of a system. That means if you can verify the system has a unique solution, Cramer's rule will be able to solve or will be able to tell you the solution value, okay, directly, okay, by plugging the corresponding value into the given formula. Okay, I will give you some idea, okay, for Cramer's rule. Okay, so let's take a look, page 22. Okay, so this section, I would like to say this is quite straightforward because you will see, I will give you the formula, and then when you plug in the corresponding value for the formula, okay, you will get the job done. Okay, but before that, I would like to introduce several concepts. Okay, so as I mentioned, okay, if there is a unique solution, okay, we can apply. Okay, we can apply Cramer's rule, but how to guarantee a unique solution, okay, for a system? Okay, theorem 4, okay, will be the answer for you. Theorem 4, what is mean by that? Okay, suppose there is a matrix A, n by n matrix. Okay, so in this matrix, there is also a linear system, okay, contain n equations as well as n variables. Okay, so if the system, okay, not if, okay, the linear system will have a unique solution if and only if the determinant A doesn't equal 0. All right, let me repeat. In the very beginning, I firstly suppose there is a matrix A associated with the linear system. Okay, associated with a linear system. Okay, and then if, and okay, not if, okay, determinant A, okay, determinant of the given matrix A is non-zero, then I can simply say that, okay, I can claim that the system will have a unique solution. All right. So maybe I put in this way, unique solution of a system if and only if determinant A doesn't equal 0. Okay, This is the essential meaning of theorem 4. Okay, or I would say this condition, okay, tell us how to guarantee a unique solution of a system by checking the determinant, okay, the determinant of a matrix A. Okay, so let's take a look. And I will tell you how to connect those ideas with the other topics, okay? Don't worry about that. So let's take a look at theorem 5 as well. Suppose there exists a linear system of the following form, a matrix equation form AX equals B, okay? And A is an n by n matrix, okay? As usual, X is a decision variable matrix, B is a constant matrix, okay, a constant column matrix, okay? So when the determinant A is non-zero, theorem 4 guarantees us there is a unique solution for the system, right? But how to find out the corresponding solution, the solution value, I mean, okay? That means we would like to find out x1, x2 until xn, okay, for the decision variable matrix X, right? So theorem 5 will be the answer for us, okay? x1, x2, and xn can be computed by the following formula. So we may firstly take a look at the general formula, okay, which is determinant of a matrix A subscript n divided by determinant A. Okay, what is meant by A subscript n? So let's take a look here, okay. A subscript n, or for simplicity, okay, I use A subscript I, okay, to denote the same thing. Actually, this is also a matrix obtained by replacing the ith column, okay, by ith column, okay, of original matrix A with the column B, okay. At the same time, we keep all of the other column remain unchanged, okay. So maybe I give you a numerical example to support this idea. Okay, in the very beginning, maybe I simply assume A is something like this. Okay, maybe I borrow the O matrix, okay, for you guys. Okay, I just pick one O example, okay? I don't give you a random example because I want to help you to connect. Okay, maybe B is a 1, 0, 0, okay, something like this. If we are going to use AI to denote the matrix obtained by replacing the ith column of original matrix A with column B, what does that mean? Suppose I would like to find out A3, okay, A subscript 3. That means the third column of A is going to be replaced by something else, okay? So, okay, that means this column, okay, is going to be replaced, right? The dash purple box is going to be replaced. Okay, this is the column. And A subscript 3, okay, means that the other column doesn't change, but the purple dash box is replaced by the column B. So it becomes something like this. Okay? Any question for the definition of A subscript I? It is also a matrix. So was it good? All right. Of course, you can also name your own example. A2 and A1 can also be another thing, right? Okay, but anyway, I picked a random matrix, okay? Okay, to illustrate what is meant by A3 or A2 or A1, okay, so on and so forth. But let me get back to the definition of, I mean, the general form of variable xn. Okay, if, okay, determinant A doesn't equal 0, that means this quantity, okay, the whole quantity, okay, xn, okay, is defined, is well defined because determinant A is non-zero, right? Okay, some number divided by non-zero. Of course, this is a unique number, right? And this corresponds to the idea why I simply call it unique solution, okay? Because each value for the x1, x2 until xn, each of them equals to a particular and unique value. And under this situation or under this case, the decision matrix, decision variable matrix, okay, will be a unique solution, okay, for the system. Do you agree? Okay, and now, previously I mentioned that, okay, I would like to help you to connect the associated concept from different topics. I hope you can still remember. I use the blue color. I hope you can still remember. In topic 2, we mentioned that determinant A doesn't equal 0 if and only if A inverse exists. Right? In topic 2, okay, we have this idea. We discussed this idea. In topic 3, okay, what we just mentioned is that determinant, sorry, I forget, okay, A here, right? Determinant A doesn't equal 0 if and only if, okay, there is a unique solution. Okay, because X equal A inverse B, right? So at this moment, I hope you guys can connect yourself, okay, with the different topic. Actually, they are referred to the same thing. Determinant A doesn't equal 0. Of course, A inverse exists. And when we apply or when we further extend the concept to the solution system, or the system of the solution, the solution of the system, we can spot that, okay, by using Gaussian elimination section, okay, we can see that X equals A inverse times B. So if A inverse exists, of course, okay, A inverse times B, okay, exists and unique, right? Okay, so you can see that why I can claim determinant A doesn't equal 0 if and only if there is a unique solution for the system. Okay, so I hope you can find the connection, okay, between topic 2, topic 3 by using the determinant of a particular matrix A. Okay, and of course, the value of the determinant doesn't equal 0. So far, so good. So can you connect different ideas together? Actually, they refer to the same thing, but we have different development. Okay, so we get to certain extent. Okay. So far, so good. And by using this formula, okay, here, this is so-called Cramer's rule. Okay, Cramer's rule will guarantee us, okay, the unique solution can be found by the formula provided here. Okay, so in the red box, okay, it provides you the general formula. Okay, and then you are going to find it by changing the value of n to 1 to 2 until the last variable. Okay, so all of the variable, okay, will be able to figure out, okay, by using this relationship, by using this method. All right, and then, okay, it also responds to the last discussion. Theorem 4 and 5 actually are closely related. Okay, are closely related, and to tell us the condition. Okay, to tell us the condition in order to form a unique solution. The condition is that determinant A doesn't equal 0. All right. Okay, the key of this part. So far, so good. And I would like to show you the proof for, I'm sorry. I would like to show you the proof of theorem 5. Okay, after the break. But let me give you a simple example first. I would like to clear the simple example. The proof, okay, may need some time to develop. Okay, so I would like to at least, okay, you can get something. Okay, you can have some takeaway, right? Okay, after this example, after this theorem 5. All right. I will get back to the proof, okay, after the break. Okay, so maybe I skip it first, okay, skip the blue part first and go to the example, okay, but I will prove the theorem 5 after the break. Okay, so let's take a look. Example 8. Okay, I would like to apply the Cramer's rule, okay, to a simple system. Okay, but before that, I hope you guys are with me. Okay, and then you will be able to tell yourself and then to answer yourself the connectivity among the topic 2, topic 3, as well as the condition for unique solution. All right. Okay, so let's go to the page 23, example 8. In this system, we are going to consider a two equations, two unknown situation. Okay, but I'm not going to say, okay, this is, I mean, the Cramer's rule may not be the best way, okay, to solve the system, because you in high school or in other course, you may simply say, hey Patrick, okay, I can use the simultaneous equation, okay, to solve the system. I don't bother, okay, for the Cramer's rule. Okay, but how about 3 equations, 3 unknowns, 10 equations, 10 unknowns? Do you still prefer to use a simultaneous equation to work on this, to work on the solution? Okay, so here, of course, I just give you the simplest example to tell you how to operate, okay, for the Cramer's rule. When it comes to a bigger size matrix or bigger size system, okay, of course, I believe, okay, Cramer's rule will be more preferable, okay, or more convenient, okay, to use. Okay, but anyway, okay, example 8 as an illustrative example for the use of Cramer's rule. So for the system, okay, of course, you can see that matrix A will be denoted as follow, 2 by 2 matrix. Okay, 4 entries are there. And can you tell me, okay, the determinant value of this matrix A? What is the determinant value of A? Yes, 10 minus 12, which is -2. Very good. So, can you tell me, okay, can we use Cramer's rule? Or what kind of solution nature of this system? Unique solutions, infinitely many solution, or no solution? A unique solution, right? Very good. Unique solution, because the determinant A doesn't equal 0. So we can safely to apply Cramer's rule, right? Any question? Okay. Okay, so we are safe to apply Cramer's rule, right? Okay, in this example. So let's take a look. And get back to the theorem 5. We know that we need to find out the matrix A subscript 1, matrix A subscript 2. Okay, I hope you can still remember the idea of A subscript 1 and A subscript 2, which means that we are going to replace the first column or the second column by using the constant column matrix B, right? Okay, so you can see that, okay, maybe I circle it out for you. Okay, so you can see that original matrix A is here. For A1, that means we are going to, okay, replace, okay, -5 and 3 by the column matrix X6, right? Okay, so you can see that, okay, the first column is gone, of A is gone. It replaced by the column matrix X and 6, right? Similarly, for A2, A subscript 2, okay, we are going to replace, okay, the second column of original matrix A, okay, by the column matrix X and 6, the entry, I mean, okay, in this. Okay, so for the idea of A subscript 1 and A subscript 2, is it okay? And the next job is to find out the determinant of these two matrices. Okay, so for the first matrix, A1, can you tell me the answer? Can you tell me the answer? Eight times -2 minus 6 times 4, right? Which is -40. Similarly, okay, for A2, the determinant of A2, which is -5 times 6 minus 3 times 8. So the answer for this determinant is -54. Very good. Okay, I see Okay, the classmate is very helpful to help us to compute the number. Thank you very much. And then, okay, we are ready to apply a Theorem 5 and get the solution value, right? Okay, so for x1, I hope you can still remember the formula, the general formula. And then we use the formula directly. So we get determinant of A subscript 1 divided by determinant of original matrix A. Okay? Okay, so let me, okay, please be reminded, okay, they are different. One is A subscript 1, okay? In the denominator, okay, it is determinant A, original matrix A, okay? So the value for this will be negative 40 divided by negative 2, which is 20. Okay, on the other hand, okay, so we get negative 54 divided by negative 2, so we get 27. Okay, so basically we solve for the system already. X1 and X2 will be equal to 20 and 24 respectively. Okay, and then you can see that, okay, the solution is actually unique. Okay, the number is unique. So I would say the solution of the system is unique, right? Okay, but here I would like to have two reminders for you. Okay, two reminders for you. Even though you can see that two equation, two unknowns case, I try to solve it by Cramer's rule, but I'm not going to say Cramer's rule, okay, is better than the original or the traditional way to compute the solution. Okay, the simultaneous equation. Okay, the method of the simultaneous equation. I'm not going to say that, or I'm not going to compare, okay, the effectiveness of the two methods. I just want to show you the effectiveness of Cramer's rule, okay, by using a simple or smaller size matrix only, okay, or smaller size linear system, okay. I just want to demonstrate how to play with the number, how to use the numerical example, okay, to tell you the way to find out the essential information, okay, for the unique solution nature, okay. When we, of course, after checking the condition, determinant A doesn't equal 0, right? Okay, the first reminder is that, okay, I'm not going to say, or I'm not going to compare which one is better, okay, to solve the system. And then when you consider, okay, to solve a even bigger solution, okay, even bigger solution, bigger linear system, okay, I hope you will be able to tell which one you prefer. Okay, of course you can also stick to, okay, the original one, okay, but I would like to give you another angle, okay, or another alternative, okay, so you will have your own answer, which one you feel comfortable to use, more convenience to use, okay. So this is the idea, okay, why I introduced Cramer's rule in this part. All right, so basically, okay, we are done for the material of topic 3. Okay, but okay, this is not the end of the class. Okay, I will prove Theorem 5 after the break. Okay, and the remaining page, again, there are several questions. Okay, practice question for you to play with. Okay, so I hope you guys to take some time to go through this, and I'm going to prove the Theorem 5 together with you after the break. Okay, seems that I already talked about an hour. So I would like to take a break. Okay, so 15 minutes, maybe around 5:45. Okay, okay. I will come back by 5:45. Okay, so after that, okay, I will tell you something. Okay, actually, I would like to tell you, okay, what is the application of the system of linear equation in engineering setting. Okay, it's just a sharing. Okay, it is not covered in the exam. Okay, or it is not an essay type question. Okay, I just want to tell you something about the engineering application. Okay, for the system of linear equation, just personal sharing. Okay, so after the break, I will tell you some. I share with you some engineering application of the system of linear equation and the proof of Theorem 5. Okay, so please come back by 5:45. Okay, 30 minutes only. Okay, so see you then. Hello guys, so let's come back. Okay, I would like to provide you with the page I covered today first. So give you some time to take a picture, okay, or to jot down some notes. So we start from Gaussian-Jordan elimination, right? Okay, so let's take a look. Okay, I start from page 17, and then for each page, it will last for 12 seconds. No, 20 seconds. 20 seconds. In the last page, I will recap some important information for the proof of Theorem 5. Okay, so page 18. Twenty. Okay, 21 is a practice question. Okay, so let's skip it. And then Parmas rule on page 23. 22, sorry. Okay, and the last page. All right. So now I would like to prove the Theorem 5. But before that, I would like to introduce some terminology first. Okay, some terminology. So in order to prove Theorem 5, you can see that we need to develop some new matrix. But actually, this is not too new, right? Okay, actually, we already use it in the definition of Cramer's rule. Okay, and I would like to borrow this kind of matrix or this kind of concept in order to support the Theorem 5. Okay, so maybe here I just take this opportunity to recap what's meant by A subscript I of B. It means that we use the original matrix A, and then I would like to replace the column I, okay, the column I of this matrix A, okay, by using the column matrix B, okay, just like the Cramer's rule, what we did, okay, for the Cramer's rule. And in particular, okay, an example is that, okay, if we have an identity matrix, okay, identity matrix I, okay, suppose I would like to replace the ith column, okay, by X, okay, by a decision variable X, okay, decision variable matrix X, okay. Of course, I can write in this way, okay, capital I, subscript I, X. Seems that too many I's are over there, right? Okay, but anyway, okay, I would like to use this kind of notation, okay, to complete the proof of theorem 5. Okay, so I will move to another. Okay, we'll move to the blank page. Okay, to write down, to share the proof with you. Okay, so please wait a moment. Okay, guys, I'll show you with a blank page, and I will try to put down the proof, okay, here. As usual, okay, I will give you some time to think, and then I will also show you a different page at the end, okay? Don't worry about that. Okay, so the Cramer's rule suggests that, okay, so maybe I put down some information, okay? Theorem 5, okay, what is Theorem 5? Actually, we want to use, okay, the theorem to find out the variable, okay, value. Okay, this is not clear. Okay. Determinant, okay, A inverse B divided by determinant A. Okay, so this is theorem 5. Okay, I want to prove this result. All right, so we are going to borrow some known matrix, right, which is A subscript IB, okay, or I subscript IX, okay, in our proof. Okay, but before that, you should be able to understand. You should be able to understand what is meant by those two matrices. All right. Okay. So now, I would like to consider the following situation. Okay. Firstly, I would like to denote. Okay. I would like to denote the column of matrix A as follows by using A1, A2, A3, AN, okay, because there are n columns, n by n matrix in general, right? Okay, so I would like to denote the column of the matrix A by A1, A2, A3 until AN. And all of the A matrix, A subscript 1, A subscript 2 means that, okay, they are the column matrix, okay, the column matrix, okay. On the other hand, I would also like to denote, sorry, how come I changed the color? Okay, I would like to denote the column of the identity matrix, okay, as follows. E1, E2, okay. To be fair, okay, I also write down, okay, E3, oh, sorry, En, okay. So let me repeat. To denote the column of matrix A, okay, we use A1, A2, A3 until AN to denote the column of matrix I. Okay, identity matrix, we use E1, E2, E3 until EN. Okay, to facilitate the proof only. Okay, now I would like to consider, okay, the following thing. Okay, I would like to consider a matrix multiplication. Okay, matrix A times matrix I, capital I, subscript I, X. Okay, so what does that mean? What does that mean? Okay, so if we decompose a bit, okay, matrix A is still matrix A, okay, but matrix I, capital I, small I, X, okay, I can write in this way: E1, E2, E3, dot, okay, X, okay, dot, En, okay. In particular, okay, this is the ith column. This is the ith column of the original identity matrix. Okay, it corresponds to the definition of I, small I, capital, okay, of this guy. Okay, so many I. Capital I, subscript I, X. Okay, the identity matrix. Okay, and in particular, the ith row is replaced by the column matrix X. Okay, so I would like to put the identity matrix in this way. Okay, so why we have this? Let's take a look. I use back the back color. Okay, so we can further expand, okay, the matrix, and we get, okay, I just multiply, okay, or to incorporate, okay, the matrix multiplication together, and then we get the first column, okay, becomes AE1, okay, and the second one AE2, and then until the last guy AE subscript N. All right, so far so good. So far so good. Okay. And now I would like to show you one thing. Okay, what is mean by A times E1? Imagine that, okay, A is original matrix A, right? E1 is the first column of the identity matrix, right? Okay. What we get actually here is, can you tell me? Or can you imagine, okay, what we are going to get from this part? A1, very good. I get the response, okay, from the group. This is A1 already. Okay. Actually, the first guy, okay, is A1, the column, okay, of original matrix A only. Okay. The second one, A2. Okay. How about this guy? How about this guy? AX is nothing but a B, right? Okay, from the definition of the matrix equation, okay, AX is B only. AX equals B, right? And then by using the same logic, okay, I get, okay, all of the results until the last one, AN. Okay, at this moment, okay, maybe you have a question in mind, okay, how to arrive at this result, okay? Okay, I will maybe you one numerical example, okay, you will have a better understanding. But anyway, okay, I would like to tell you, okay, under this result, under the current result, actually, this is A subscript I, B, right? So let's take a look. This is A11. This is A1, A2, until last guy AN. Originally, okay, if we remember clearly, okay, all of them represent the column of original matrix A. But in the ith column, I replace, okay, the ith column by matrix B, right? Okay, so this is the definition of this matrix. This is the definition of this matrix, right? Right? Am I correct? All right, so you can see that, okay, we can form a relationship like this, okay? So I will add a new page, okay? So I will have a relationship like this, A times capital I, small I, X, oh, sorry, X, okay, equals, okay, capital A, small I, B. Okay, so this is the relation I need. And then the next job, okay, then the next job, okay, do remember what is the key of our problem. We want to find out all of the x, right? We find all of the x1, x2 until xn, okay, in order to complete, okay, the decision matrix, right? Okay, x equals x1, x2, dot, 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 until xn, right? Okay, okay, so if we can solve for x1, x2 until xn, that means x, the decision matrix x can be done, right? Okay, now I would like to take the determinant on both sides. Okay. All right. And then I decompose the result on the left-hand side into two parts. Oh, sorry, I used bracket. Okay, seems that the right-hand side, nothing changed. Okay, nothing changed. All right. So my question, my next question is, what is this? What is this guy? What this guy? Okay, very good. You get it. This is x. Okay, so in order to make it more visible, okay, so maybe I write it here. Okay, very good. I'm super happy to see you get the right answer. So actually, okay, for the capital I, small I, x, okay, actually it represents something like this, right? Okay, the first column is still I, 1, 0, 0, 0, 0, okay, for the original identity matrix. Okay, secondly, okay, something like this. Okay, after several column, okay, after several column, okay, I would like to replace the ith column of original identity matrix by, okay, by x, right? Okay, so okay, in particular, this is the ith column. Okay, this is the ith column. So good. Okay, let me complete the remaining part. Okay, so you can see, okay, the last row may be something like this, right? If we are going to take the determinant, okay, of this matrix, okay, so what will you get? I would like to suggest you guys to consider the ith row, okay, the ith row, okay, okay, the ith row correspondingly, okay, it gives you the xi, the value of xi here, right? And then I would like, oh, sorry, this is not clearly presented, okay. Actually, this is dot, okay, but I write just like a 1. Okay, so now I would like to suggest you to decompose or to find out the determinant value, okay, by using the ith row, all right, because it consists of many 0, right, except the ith element, okay, the ith element, Okay, so when you expand or when you find out the determinant of this matrix, okay, so you will get, okay, the determinant, okay, of, okay, will simply equals xi. All right, will simply equal xi. Okay, you can use the cofactor, the minus, something like that, okay, to find out the determinant. Okay, please go to the corresponding topic. Okay, you will be able to find. Okay, so now, okay, I can, okay, to add some new result here. So previously, determinant A times determinant, okay, capital I, small I, x equals determinant, okay, AIB, right? But determinant, okay, the second guy, okay, this guy, it is nothing but xi, right? After the after the computation of determinant, and then we have the following result. And then when we rearrange the term a bit, okay, xi equals determinant divided by determinant A. And this is Cramer's rule. Okay? So when you substitute I to be different integer, okay, for example, 1, 2, until n, you will get all of the A1, A2, until AN, okay? All of them will be available by using this formula, right? Okay, so, okay, we get the result and we get the proof of theorem 5 done, okay, by using this idea. Okay, so far so good? So far so good? So this is the proof of theorem 5. All right. And I would like to show you all of the pages if you wish. Okay, so you may want to take a picture. Okay, if you need. Again, for each page will last for 10 seconds. Okay, the second page. Okay, and then the third page. So this completes the proof for theorem 5. Okay, I will show page 1 again later. Okay. So can I go back to the proof of, I mean the page 1? Okay, in this page. Okay, this is the page 1. Do we need to prove in exam? In the exam, everything will be covered, right? Okay, so far so good. Okay, so we complete the proof for theorem 5. And as I mentioned, okay, I would like to share with you some engineering application for the system of linear equation. Okay, of course you may have, I'm not so sure, okay, whether you make up your mind, okay, for the major selection, okay, at the end of this year. If you are going to choose, for example, ECE, the electronic electronic engineering, right? Okay, so you may have opportunity to get in touch with the electric circuit, right? Okay, not to mention, okay, in the electric circuit, you need to determine the current, voltage, resistance, right, in the circuit. Okay, so when you are going to consider a complex or complicated circuit, okay, you want to find out the how to say this, a simple circuit, okay, simple electric circuit, okay, it involve quite a number of resistor, a current or voltage over there, okay, and then you will be able to find out, or you will be able to model this kind of situation by using the system of linear equation, and then by solving the system, okay, or you cheat the variable, for example, to be a current, okay, so you will be able to find out the current at different branch, okay, or different the current across different resistor, for example, something like this. Okay, so this is one of the engineering application, okay, for system of linear equation. And I would say this another interesting or important application in engineering is stemmed from the system engineering. Okay, for example, if you are interested in the transportation logistics, okay, suppose you are going to model a transportation network. Okay, of course, you are going to put down a series of linear equation to see or to model the supply and demand, okay, over the transportation logistic network, and then you are going to model, okay, the supply and demand situation, okay, and then you are asked to, for example, you are asked to figure out, okay, how many shipment or how many cargoes you need to ship, okay, from one point, from the starting point, okay, to another point. Okay, but how many cargoes or how many products, okay, you need to shift in the middle of the network. Okay, you can solve it or you can model it by the system of linear equation, and then you can solve, okay, or to get the desired answer by using, okay, the logic or the idea of the solutions, the solution nature. Okay, we just described it in topic 3. Okay, so you can see quite a number of interesting application, engineering application. Okay, they are using the system of linear equation, and then if you are going to take some advanced course, for example, optimization, okay, in second year or in your postgrad study later on, you can see the linear programming will also pay so much emphasis on a system of linear equation, okay, in the constraint or even in the objective function. So you can see quite a number of linear equation, and then you are asked to solve this kind of problem, okay, by using the technique you learned here, okay. So I hope you will find it interesting and motivated why you need to pay more effort in topic 3. Okay, so you can see we spend quite a number of time, okay, to complete the whole part of material of topic 3. Okay, just some sharing. Okay, I'm not going to say we only limited to the application in ECE or the system engineering. Okay, I'm not going to say that. Okay, but to the best of my knowledge, okay, I see quite a number of interesting application over there. Okay. Okay, so far so good. So far so good. Any particular question? Okay, until now. And we've basically finished all of the materials for the topic 3. Okay, and when we come back on Wednesday, we will start topic 4. Okay, another big topic, very big topic. And at this initially, okay, we assume we will cover everything of the topic 4 for the coming midterm exam. Okay, but I also need to consider, okay, the progress from other sections, okay, to see other professor will they cover everything, okay, before the midterm. Otherwise, okay, we may only need to cover some of this. Okay. All right. So any particular question? Because I will have a TA meeting after the class. So if you have no particular question, so I may need to end here.